I think all the students have joined by now, so we can start the session. So hope your lectures are going smoothly with IITians Hub so far. Right. So we have had an introductory session earlier in which we discussed about the some of the general aspects of the subject of physics, and we discussed a little bit about the method of physics, of the method of mathematical modeling, etc. in physics. So continuing that discussion ahead, we will see that two aspects of applied mathematics which become very, very important in physics. They are vector analysis and basic calculus, or calculus as we call it. And hence, that is what we will start with in our physics syllabus. On the one hand, one track of vector analysis or vector algebra, you're being taught by Hemant sir, and I will be teaching the portion of calculus, or what we can call basic calculus. It will initially appear like a branch of mathematics, but we will be studying it in such a way that you see it is closely related to physics, and its application is entirely for the subject of physics mostly. So we will study the fundamental principles of calculus, but immediately as we are studying it, we will see how the application happens in the context of physics. Okay. So let's begin. Okay, so as I was saying, calculus is essentially a branch of mathematics, but which has major application in physics. Okay. So calculus is a branch of maths that deals with two essential concepts. It deals with rate of change, something we'll be discussing in detail in today's session. Okay. And the area under a curve, something that we'll be discussing subsequently. Okay. So in fact, calculus is divided into two portions. Differential calculus, as you might have heard, and integral calculus. This is the one that deals with rate of change. And this is the one that deals with area under a curve. So just to give you an example of how this applies in physics. For example, in physics, we say that acceleration is the rate of change of velocity with respect to time. Okay. Or we say that the net force on a body equals to the rate of change of its momentum. That is the statement of Newton's second law. Okay. Whereas how this area under the curve and integral applies, for example, is that displacement is the area under the velocity time graph. or impulse due to a force equals to the area under the force time graph. So if you're a little bit unfamiliar with these second two examples, these ones, don't worry, we'll be coming back to them very soon. But I'm sure most of you are familiar with the first two examples. That is the concept of acceleration, or the definition of acceleration being that it is the rate of change of velocity with respect to time. And the definition of net force, or rather the statement of Newton's second law of motion, that the net force acting on a body equals to the rate of change of its linear momentum of it, or simply the rate of change of momentum. Okay. So progressively we are going to see that when we start looking at these type of concepts and these type of definitions in more detail in terms of the mathematical application in real life physics problems, then we need an additional machinery in mathematics. What we know till now in terms of simple algebraic operations like addition, subtraction, division, etc., they're not going to suffice. They're not going to be enough to deal with the maths that we have to generate ahead for application of these kind of definitions. And that is where calculus comes in. And the interesting thing about calculus is that calculus was invented largely by Newton and another scientist called Leibniz. Leibniz was a French guy. So it was invented during their study of physics. So as Newton was developing his ideas in classical mechanics, or what is now called Newtonian mechanics, okay, as he was developing those ideas, as he was formulating the laws of physics in terms of mechanics, okay, he developed this area of mathematics to deal with the equation solving part of it, or to deal with the mathematical expression of mechanics. Okay, so Newton was one of the co-inventors, you can say, of calculus. Okay, last time we were discussing that mathematics is largely an invented subject, whereas physics is a subject that is derived from natural science because it describes what we see in the physical universe around us. Okay, whereas mathematics is out of pure imagination and pure invention. So Newton invented calculus partly as he was trying to describe the laws that he was discovering and describe them in mathematical language. Okay, and as the story goes, like initially Newton and Leibniz, you can say, collaborated on the development, and there was correspondence between them and all. But eventually there was also some controversy between Newton and Leibniz, okay, over who was taking the credit for development of calculus. And true to that time, like eventually they were not extremely good friends or anything like that. Okay. So as the legend goes, around 1660 or in that decade, sometime in that decade, Newton had that famous Eureka moment when he discovered gravity. All of you would have read or heard about that story, that he was sitting in his garden, and as he observed an apple falling from a tree, he realized that something is pulling it down. Okay, and hence there is something like gravity, or there is some kind of attractive force that the earth or the surface of the earth is applying on that particular object which is in free fall. Okay. So it's as the legend goes that he discovered gravity in a moment like that, but the truth of course behind that is that there were years of analysis, there were years of a lot of scientific deduction which led him to that particular moment where he realized that there is force involved in that particular motion. So the story of calculus almost is as old as that and develops along with that. Okay. So we will discuss later today how the story of the falling apple also has a message in it as far as the concept of rate of change is concerned, and how differential calculus story actually started from that point onwards only. When Newton started studying the motion of objects which are accelerated. Okay. So before we proceed, I would like to reiterate that you should have a separate notebook for each of these tracks of the subjects that we are studying. So for example, my track of physics right now is calculus. So you should maintain a separate notebook for calculus, just as you should maintain a separate notebook for vectors, which is the other track of physics. Okay. don't mix them into one notebook because you'll find it difficult to revise later. The second thing is you don't need to make very detailed class notes during the lecture, because as I've told you before, that I will be sending you the PDF of the whiteboard class notes. So you can fare your notes later from that. Just, you can keep a notebook and jot down the important points, because jotting down points always makes things more firm in our memory, okay, and more organized in our mind compared to just listening or just seeing. Okay, so do keep jotting down some rough notes, but you don't need to make the fair notes while in class. Your concentration should be on the learning part while we are in class, and you can make your fair notes later. Uh, of course, we will be solving some mathematical numerical problems and all. And while we are solving those problems in class, I'm solving them on the board, or I've given you some time to solve. At that point of time, you should try and do a detailed solution of those things yourself, because practicing maths is going to be one of the key things, and we should keep doing that as much as we can. So I will give you time during solving of the questions, and for that you can solve the question step by step. Okay. The other thing is that at the moment you refer to your module, okay, in physics, the module number 1 that you've received, which is called Useful Mathematics of Physics. So the first section of that module is vectors, and the second section of that module deals with calculus. Okay. Okay. Most of you would have you might be having the physical copy of the module which was given to you at the time of admission, or if you were not able to come to the office during the admission time, then you at least have the PDF of this module which is shared in the group. Okay, so module 1, it is called the Useful Mathematics of Physics. And it essentially has 2 sections: vectors, okay, and calculus. So you can start referring to this, okay, for this section of physics that we're doing. I will not be asking you to refer to any other reference book at the moment. When we finish calculus, or at least finish differential calculus, that point of time I will refer to you to some additional reference book which you can start referring to. So let's come to the concept of differential calculus, and to understand that, the first section of calculus rate of change. We will talk about this simple principle of rate of change. Okay. So the physical example we will take to understand rate of change is, we will talk about the speed, okay, of a body moving along a straight line. Okay. Now, can anybody tell me how we define speed?
Distance covered in a particular time period.
Distance covered in a particular time period. Okay. Any other definition? That is correct. And but anybody else has a definition in some other words or something more specific?
The rate of change of distance with respect to time.
Can you speak a little bit louder, Beta?
The rate of change of distance with reference to time.
The rate of change of distance with respect to time. Okay. Anyone else?
So the rate of change of position of an object.
Okay. Rate of change of position of an object. Okay. Okay. That's an interesting.
In any direction.
Okay. Okay. So is that speed or is that velocity?
So speed, no?
Velocity.
Okay. We will see that there is a slight technical difference. Okay. When we talk about rate of change of position, it actually becomes displacement. Whereas when we talk about distance, it is the path length. You're understanding my point, Beta? Okay. So for example, if an object is over here, okay, at some point of time, now I'm going outside straight line motion, okay, and suppose it goes on a path like this, and it eventually reaches this point B over here. Okay. So the The distance covered is this path length. Okay. But what is the displacement? The displacement is the shortest path, that is a straight line joining A and B. So this is the displacement. Okay. Whereas suppose the actual path the particle took was this one, then this dotted line's total path length is nothing but the distance. Okay. So when we say the change in position, it actually means A to B. Okay. So that means the displacement. So if I say rate of change of position with respect to time, I'm actually calculating rate of change of displacement with respect to time, which is actually defined as velocity. Whereas if I talk about rate of change of distance with respect to time, then I'm talking about speed. Okay. But anyhow, at this stage, it doesn't matter so much, because if we are talking about straight line motion, okay, then distance and displacement will be the same as long as the particle is not going back and forth. Okay. If a body is going along a straight line, but in such a way that it's not changing direction in between. So as it is going from one point to another along the straight line path, it does not reverse its direction. It's not going like this and then coming back. This is not happening over here. Okay. What is happening is it's continuing in the same direction along the straight line. So if that happens, then we can say that distance is the same thing as displacement. So we don't need to worry about that. Okay. So yes, so we have established through some answers that speed, for example, can be written as distance divided by the time interval. Okay. Or it can be expressed in words as rate of distance covered with respect to time. Okay. Now let me cite an example. Now as an example, suppose we are in a vehicle which is traveling along a straight line. Okay. How do you measure speed? How do we do the measurement of speed? Any idea?
Sir, we calculate the distance traveled by it and then
Distance
divided
upon
by
time.
time.
Okay, so we might do something like this, that suppose this is where we started at. So at that point of time, the time was, let's say, exactly 12 noon. Okay. And suppose we can see that we reached here at a time of, let's say, 12:30 p.m. Okay. So if we can calculate this distance, let's say S, okay, then we will say that the speed is this distance divided by the time difference between 12 o'clock and 12 noon and 12:30 p.m. That's what you're saying, Vita? Okay. Anything else? Like any other way that we measure speed? Like while we are traveling, okay, there is an instrument now in the car which shows us something. Yeah, speedometer, correct. Sambhavi has mentioned. Okay. So if you're in a typical journey like this, what does the speedometer generally tend to indicate?
Instantaneous speed.
Instantaneous. Sir.
Matlab, does it remain constant typically, like unless very extreme
No.
case? No, no, it changes from instant to instant. No?
Instantaneous speed.
Yeah. So you will notice that the reading of the speedometer continuously changes. Now, when we are accelerating, it increases. When we brake or when we decelerate, it decreases. And from moment to moment, it changes. Okay. So that reading of the speedometer at a particular instant of time, that is called what? That is called the instantaneous speed, like you have correctly mentioned. At some particular point of time t, which is greater than, let's say, this time t1, and less than this time, let's say t2, which is the entire journey. Okay, we have instantaneous speed. So how will we describe that? It is the speed at a particular moment, right? It is the speed at an instant of time. And that is what the speedometer measures. In this particular example, it is the speedometer's reading at that instant. Whereas what was the other thing that we were measuring when we said that?
Speed.
Yeah, sorry,
Average
come again,
speed.
beta.
Average speed.
Yes, very good. That's correct. Okay. As far as measurement of speed is concerned, we can have one type of measurement which is instantaneous speed, and the other type of measurement which is called average speed. Now, can you define average speed?
Total distance
Total
covered
distance
divided.
traveled upon total time taken.
Very good. That's so it is basically like a ratio. It is the total distance in a certain time interval. Okay, in a specific time interval. Okay, divided by the time or the time interval. So, for example, here I might, if I know this distance s, okay, then I will say that okay, average speed for the time interval t1 to t2 will be equal to the distance divided by the time interval. So that will be s divided by t2 minus t1. So suppose this s comes out to be whatever, it comes out to be, let's say, 20 kilometers exactly. Okay, so then this will become 20 kilometers divided by 30 minutes, or you can see that it will become 40 kilometers per hour. So we can say that the average speed during that time interval from 12 to 12:30 p.m. was equal to this. Whereas, for example, at this moment, if the speed was maybe 60 kilometers per hour, at a particular instant of time, t equal to, let's say, 12, 15, and 30 seconds. Okay. So, for example, we will say that the instantaneous speed at t equal to a certain instant, so that is 12, 15, and 30 seconds, that was equal to 60 kilometers per hour. Okay. So now you can see that we have got a very good idea of how we would measure this average speed. Okay, because we can always measure the total distance from where we started to where we ended up from T1 to T2. Or even if we don't want to measure it, separately like that, we have a device in our vehicle which is called the Myelometer, right? Which is along with the speedometer that keeps measuring the total number of kilometers that the vehicle has moved.
It's an odometer, right?
Odometer, or it's called the Myelometer, right? Okay, so you can set it to 0 when you started the journey. Okay, and when you finish the journey, you know exactly how many kilometers. I mean, exactly in the sense that it's up to the accuracy that the odometer or the Myelometer has. In typical vehicles, it's up to 1/10 of a kilometer, right? So it will tell you the total number of kilometers, and you can always have a stopwatch, or you can use your wristwatch or whatever. So that will also give you about an idea of the total time in the journey. So you can just divide the total distance divided by the total time, and that will give you the average speed. Okay, but how do you think instantaneous speed is measured? For instantaneous speed, you need the device called the speedometer. Okay, it's the reading of the speedometer. How does the speedometer read instantaneous speed? And what actually is instantaneous speed?
Sir,
Like
it
here,
calculates the rate of change of momentum of the car.
no, rate of change of speed, momentum nahi hai beta, because what is the unit of instantaneous speed? Is the same as average speed, na? It is meter per second or kilometers per hour.
Sir, so it will actually take how much the distance has changed in a very short amount of time.
Yes, that's a very good. Okay. So
An
what is the
instant of
difference
time.
between average speed and instantaneous speed? Yes, it's correct to say that it is the speed at a particular moment or a particular instant. But how does the speedometer actually end up measuring that what is the speed at that moment? And what is meant by that? Okay. So first of all, what is meant by saying that, okay, the instantaneous speed is 60 kilometers per hour? It doesn't mean that it's going to cover 60 kilometers in 1 hour, or it doesn't mean that it's going to cover 30 kilometers in 1 hour. It means that at that moment, the rate at which it's covering distance is such that, suppose, okay, now listen very carefully. It means that suppose the motion continued uniformly, that is, we neither brake nor accelerated, then in the next 1 hour, we would cover 60 kilometers. But it doesn't say that we are going to cover 60 kilometers in the next hour. It just says that at that moment, okay, the way we are covering distance with respect to time, that is this instantaneous speed at which we are going, it is such that suppose we don't brake or we don't accelerate, we continue in the uniform motion, then we would have covered 60 kilometers in 1 hour. So that's one way of interpreting instantaneous speed. Whereas what average speed says, 40 kilometers per hour, it does mean that over that half an hour or whatever interval of time, we covered distance in such a way that if we went at a uniform speed, then that uniform speed would have been 40 kilometers per hour. Understood the difference? Now, if we say that average between 12 and 12:30 is 40 kilometers per hour, it means that the way we covered this distance, suppose we had gone at a uniform speed, then that uniform speed would have been 40 kilometers per hour. Whereas the instantaneous speed at a moment, what it says is that at that instant, the rate at which we are covering distance, at that very small instant of time, it is such that if we don't accelerate or if we don't decelerate, or in other words, if we continue in uniform motion, then we will cover 60 kilometers in the next 1 hour. Okay, so hope this first point is clear to all of you. Now we come to the second point, that how we actually measure the instantaneous speed. So yes, somebody said that it is, I'm forgetting who exactly, sorry, but I had a very good answer that instantaneous speed is the rate of distance covered with time in a very short interval of time. Can you just tell me who answered? Like, person, sorry, I missed the name.
Sir, you had asked about that speedometer. I had said.
Yeah, Darsh, it was your answer, right?
Yeah.
Okay. So now can you tell me how the speedometer manages to do this? Okay. You're saying that instantaneous speed. How do you think the speedometer measures this? It is the rate of distance with respect to time, right? In a very short interval. That's what you said? Or at least that's what you meant?
Yeah.
Okay. So how do you think the speedometer measures this? Any idea?
Rotations of like the wheel and
Yes,
then
sir,
they
probably.
calibrate it.
Yes, very good. So for example, in the case of a speedometer, okay, the speedometer is basically a device which is hooked to the axle of the wheel. Okay, so it measures the rate at which the axle of the wheel is rotating, and therefore it can measure the rate at which the wheels are rotating. So it measures the rate of rotation. In fact, in language of mechanical engineering or automobile engineering, you might have heard the term RPM. Right? What is RPM? It's rounds per minute.
Rotations per minute.
Yeah, rotations per minute or rounds per minute. So it measures the rate of rotation. So from the RPM value, it can measure, it can calculate basically the time period per revolution, right? For example, if we know that if a wheel is making, if rotation is at the rate of X, where X is some number, RPM, rounds per minute. Okay, so that means it's making X cycles per minute. So it makes X cycles per minute or in 60 seconds. Okay. So therefore, what will be the time period per cycle? It will be X divided by, or it will be 60 divided by X. This will be the time period for one revolution. Okay. So you can imagine that if, for example, the rate of rotation is, let's say, 180 RPM. So it's making 180 revolutions per minute. So that means what is the instantaneous time period? That is, one rotation is happening in how much time? It is happening in 60 seconds divided by 180. So it's literally happening in 1/3 of a second. So 0.33 seconds. So this is a typical example. Okay. Now, how does it convert this information of time period of rotation into instantaneous speed? That is rate of covering distance with respect to a very short interval of time. How does it, what other principle it makes use of? Can anybody tell me the specific name of the type of motion that a wheel undergoes when it's moving on a surface?
Rotational motion.
Frictional motion.
It calculates the circumflex motion.
Sorry, that's an interesting answer. Come again, I couldn't hear better.
Translatory motion.
Translatory motion, but is it only translation?
No, it's both rotation and translation.
Yes, very good. It is a combination of rotation and translation. So is there any particular name for that type of motion? Okay. Actually, let me give you a hint. Like if the soil on the floor is very loose, or there is like slush, okay, the wheel tends to slip. That means it rotates more than it translates, or it might only be rotating also if it's not translating at all. Right, so that type of motion is called what? Slipping. Or if we jam the brakes very hard, then it might stop rotating, but still it might skid on the surface. That means it's only translating. So if the wheel is only translating but not rotating at the same time, then that's an example of slipping. Okay. Or if it is rotating but not translating, so it's in one place only but it's going round and round, so again it is slipping at the surface. Okay. But if it is doing what is called non-slipping motion, yeah. What was the answer, beta?
Rolling.
Rolling. Very good. So there's a specific type of motion which is called rolling. So in that rolling motion, what happens is that there is a combination of rotation and translation such that it does not slip. The point of contact on the floor net does not slip. So rolling motion, that is the motion that the wheel is doing, unless it is slipping because we have jammed on the brakes too hard, or we are starting at a position where the soil below is very loose, so it's not able to grip. There isn't sufficient friction. So instead of rolling, then it is it is slipping on the surface. Okay. So rolling is a specific type of motion. It is a combination of linear motion. Okay, what we will later see is defined as the translational motion. That means the whole wheel is moving with some speed v, and rotation. That means the wheel is rotating about its own axle like this, such that it does not slip. On the ground. Okay. So in normal circumstances, that is how a car is moving, that it does not slip on the ground. Okay. So if it does not slip on the ground, then can you tell me that when it completes one cycle, by the time the wheel completes one cycle, how much distance will it cover?
Circumference of the
Complete
wheel.
circumference.
Very nice. That's very good. That's correct. Okay. So it will cover in one revolution or one cycle, it will cover a linear distance on the ground that is exactly equal to its circumference. Okay. And there's a very easy way to visualize this. Okay. Just imagine that what we have done is you're doing an experiment where you have laced the outer circumference of the wheel with some paint, okay, with some sticky kind of paint, and now you roll it on the ground for one revolution. So by the time you roll it for one revolution on the ground, you will see that this point A, which I've labeled over here, now it goes from here to here. Okay. So after some time, let's say here, so eventually by the time one revolution is completed, it is back on the ground. So by the time one cycle is completed, the point A is back on the ground over here. So what will happen is, apart from the point A, all these points over here, they are coming into the contact with the ground once. Like for example, if this point B was over here, then B is coming into contact with the ground at this point of time. If this point C was over here, so it's over here right now, so it might come in contact with the ground once like this. So like that, every point on the circumference from A back to A over here will come in contact with the ground at some point of time, going from here to here. So by the time A is completely back here, all the points on the circumference from A back to A will have come in contact with the ground once. So the total length of the paint mark, okay, you put some sticky paint on the surface of the wheel. So that sticky paint is leaving a paint mark on the ground. So the total length of that paint mark will become how much? It will become equal to one circumference if you completed one cycle. So that's a simple way of trying to visualize how we can show experimentally that a rolling object, whether it's a sphere or a cylinder, or a disc or anything like that, if it is rolling on the ground, then in one cycle, the linear motion results in a distance traveled, okay, of equal to 1 revolution. So S will be equal to 2 pi r in 1 revolution of the rolling motion. So now you can understand how the speedometer actually ends up measuring the instantaneous speed, because through the RPM, rounds per minute, it is measuring the time taken per cycle. So the time taken per cycle is like this: 60 seconds divided by X, okay, where X is the number of rounds per minute. So now it knows the time taken to go from here to here. And because it knows the radius of the wheel, I mean, it's calibrated in such a way that it knows the radius. So it can make a measurement of the speed during this cycle. So the speed during this cycle will become 2 pi r divided by the time period. Okay. Now you can imagine that typically the time period is very, very short, something like this. So in context of the whole journey that we're talking about, this time period that we are saying is a very short interval of time. So if it's a short interval of time, it's more or less showing us what? It is showing us the instantaneous speed at that moment. Okay, at that very short interval of time during which the tires are making one single revolution. So for that very short interval of time, it is measuring the rate of distance with respect to time. Hence, according to the definition of speed, we will say it's which type of speed. It is instantaneous speed, because it is at that instant. Okay. So now we come to a more technical definition of the concept of instantaneous speed versus average speed. So we will see that speed, which in general we can define as rate of distance with respect to time. Now we can divide that into two types of measurements. One is the instantaneous speed, which we might denote with the symbol V. So the instantaneous speed we will write like this: it is delta S by delta T, where delta T is specifically a very short interval of time. So because it's a very short interval of time, the instantaneous speed is speed at an instant. Okay. Whereas when we talk about average speed, it is the average speed for, you can say, a specific interval of time. Instead of for a specific instant of time, it is defined for a specific interval of time, say T1 to T2. So the average speed will be defined as delta S by delta T again. Okay, but this time delta T is a specific interval of time, T2 minus T1. Instead of being a very short interval of time, it's a specific interval of time between two distinct instants. Okay, so it is basically equal to S2 minus S1, the total distance covered in the total time T2 minus T1. So this is how we would mathematically describe average speed for a specific interval of time T1 to T2. And this is how we would describe instantaneous speed at a particular instant of time, let's say T0. Okay. So I'll just minimize this for a moment. Okay. You can just go through this section once, jot down any key points if you want. But more importantly, just go through this discussion, this section once, and just confirm if you have any doubts or any difficulties understanding any point. Yes, that is correct. That later we will see that for the exact measurement of instantaneous speed, the calculus type of definition of instantaneous speed, the delta T in the denominator in my second definition of instantaneous speed, the delta T should be so small that mathematically we say it approaches zero or it tends to zero. So that will give us the proper differential calculus definition of instantaneous rate of change. I'm coming to that very soon. But right now, for example, I'm just talking about like a practical sort of measurement type of way of instantaneous speed. So practically, how does the speedometer measure the instantaneous speed? It measures the distance covered in one revolution, which technically is a very small amount of time. It may not be tending to zero, but it's still a very small interval of time. Compared to the total time of the journey, it will be a very small interval of time.
So can you explain slipping motion once again?
Matlab slipping is na, just imagine that your car is stuck in in kichad, in slush. Okay, and one of the tires is like in a pit of mud like that, in a pit of slush. So what will happen? The wheel will tend to keep rotating as you transmit, through the engine. So as you press the accelerator, the wheel will tend to spin, but because it's not gripping on the ground, it will either move very slowly or it will not move at all. And if it doesn't move at all, you're in trouble, because you will need to physically remove the mud and place a plank over here or something to get that wheel out of the slush pit. You're following now, Vita? Can you imagine that situation?
Yes, sir.
Okay, so that is one example of slipping. Another example of slipping would be something like this, that, imagine you have a very smooth surface, like this surface of a well powdered carom board. Okay, and you take a spherical object or a cylindrical object, like you might take a billiards ball, and you push it with your hand like this. So you give it an impulse like this. Now, if the surface is perfectly smooth, you will see that as the ball goes, it does not rotate. It simply just goes like this. So if you marked a diameter or two like this, you'll see that the motion is like this, which means that it is only translating. It is not rotating. So then you will see that the point of contact is skidding in this direction. Whereas if you repeat that experiment on a surface which is rough, you will see that when you give this a push, okay, it will move in such a way that this is what is happening. It's rotating also. Along with the translation, it is also rotating. So it's going like this also, but at the same time, it's going like this. And if there is sufficient friction to prevent slipping, you will see that this type of motion is happening, the rolling type of motion, that the point of contact does not slip at all. So in one cycle, it covers a distance of 2 pi r. So that is the difference between rolling, where there is no slipping at the point of contact, versus this type of slipping, where there's only translation or only linear motion, or this type of slipping, where there is this type of slipping over here, where there's only rotation, no linear motion is happening or no translation is happening. So those are two examples where an object is in contact with the surface, but the point of contact is slipping. Whereas rolling is the example of an object which is moving on a surface, but is moving in such a way that the combination of rotation and translation means the point of contact is not slipping. Okay.
Okay, sir.
Yeah. Now, in a future chapter called rigid body motion or rotational motion, we will look at this whole business of rolling versus slipping in much more detail with proper equations and all that. But till then, you just think of this intuitive sort of method of understanding it. Okay. Okay, so let's come down to this part now. You can say the so-called definition of the two types of speed, instantaneous speed and average speed. So later you will see that we'll be changing these symbols. Over here, we won't be calling this delta S by delta T anymore, because we are using this specific condition that delta T is very small. So in fact, in the calculus definition, we'll say that delta T is so small that it is tending to 0. So then the symbol changes from delta S by delta T to ds by dt. But I don't want to confuse things just now. So we will just keep the definition of instantaneous speed as a word definition like this, that it is distance with respect to time for an extremely short interval of time. Okay. So when I say for an extremely short interval of time, what I basically mean is that from a measurement perspective, the shorter the interval of time, the shorter the value of delta t that I'm using in my measurement, the more accurate will be the measurement of instantaneous speed. So if we are using, let's say, a combination of instruments to measure instantaneous speed, and a particular instrument is able to measure it for an even shorter interval of time compared to the other one, then the one which is measuring for a shorter interval of time will give me a more accurate measurement of instantaneous speed. It will give me a better measurement of instantaneous speed. For example, apart from speedometer, you would have heard of an instrument called a speed gun. A speed gun is used to measure the instantaneous speed of moving objects, right? Can you give me an example of anywhere where speed guns are used?
So cricket match when bowler is bowling the ball.
Yes, very good. It is used in sports, for example. Okay, in sports where there is the importance of the velocity or speed with which a ball is moved. So, for example, in cricket, bowling, in tennis for the service speed, etc. Okay, these kind of things. Anywhere else we use a speed gun?
Sir, also when someone is
In the
going too
traffic
fast,
police.
so the
Yes, sir,
police
traffic.
uses the gun on them.
Traffic police, yes, I missed the other one.
Radar speed gun.
Yeah, Vineet, you were saying something?
Yes, sir. Radar speed gun used by the traffic.
Radar speed gun used by?
The traffic police.
Yeah. Okay. It's also used, okay, so by traffic police. Okay. So how do you think a speed gun works? It measures what? The speed gun also measures instantaneous speed, no?
Yes, sir.
Yeah. Tell me any idea how a speed gun works?
Sir, it sends a narrow beam of some frequency and it calculates the time by which it returns.
Yeah. So there are various types of speed guns. So for example, one is the ultrasonic one, where basically it's like a radar. So it sends a sound signal which is ultrasonic. That means the frequency is higher than the audible range of sound. Okay, so we don't hear that signal, but the moving object interacts with that sound wave. Okay, and it creates a disturbance in the sound wave in such a way that, okay, there is another type of speed gun which is, you might have heard, infrared sensor. Infrared sensor based speed guns. Okay, so for example, you want to measure the speed of a ball being thrown, I mean a ball being bowled in cricket, or you want to measure the speed at which a vehicle is covering, is moving on a road. Okay, so let's say this is the road, and on this a particular vehicle is moving like this. So what you will have to measure using an infrared sensor is that on one side of the road you will have a panel with infrared LEDs which are emitting light in this sort of direction, infrared light in this sort of direction. Okay, and on the other side, so you will have infrared LED panel which emits that invisible infrared light in this direction, and on the other side you will have the infrared detector. Okay, now what happens is that as the vehicle passes through this panel, okay, this panel has a specific length and it blocks light for a specific period of time. Okay, so if the length of this is very, very small, okay, then it is able to measure the rate of distance covered with respect to time for a very small distance and therefore a very small interval of time. Okay, so this will tend to work better the smaller the size of the object also, because it should block it for, you know, that instant when a point on that object is blocking the sensor. So this kind of thing works better for a moving ball or a moving particle compared to a moving object like this. But again, using a combination of LED panels like this, actually using a combination of panels and using a software, you are able to actually correlate the information about how different points on the vehicle are moving. So you can actually track the rate of change of distance covered by a particular point on the vehicle and not the whole vehicle put together. So you are able to measure. Okay. So what I'm trying to say is we can use different type of technologies like radar, infrared detectors, okay, or the concept of a simple speedometer. Of course, that has to be an onboard device. It's not outside the moving vehicle, which measures the RPM, etc. But whatever devices we are using, ultimately the accuracy of that device is determined by how short an interval of time in which it is able to measure the distance covered. So if for example, we have a very high-end device like an infrared detector with a combination of panels, it might be able to detect for a time interval as short as 1 microsecond. So that will be very, very accurate. Compare that with, let's say, the mechanical type of speedometer, which is measuring the instantaneous speed for a time interval of something like maybe 1 millisecond. So 1 millisecond is 1,000th of a second. It's 10 raised to minus 3 seconds. Whereas 1 microsecond, as you know, is 1 millionth of a second or 10 raised to minus 6 seconds. So you can see that there's a world of difference between the accuracy of this one versus this one, because this is measuring in 1 millionth of a second, okay, whereas this is measuring comparatively only 1,000th of a second. So this is much, much more accurate than that one. So as far as the principle of measured value of instantaneous speed is concerned, it all depends on the technology or the physics of the technology that we are using to determine or to measure this value of delta S by delta T. The more short the value of delta T, the shorter the value of delta T, the more accurate my measurement becomes. Okay. So practical definition of instantaneous speed is that it's distance covered in a very, very short interval of time. And practically whatever device we are using, the shorter the interval of time, the more accuracy of the measurement is, right? So hope this point is clear to all of you. Now, let us discuss this in context of two examples of motion. And again, those examples of motion will be in context of Newton's laws. Okay. So now we are again going back. Yeah.
Can you explain how a speed gun works?
Yeah. So, for example, the kind of speed gun that is used to measure in sports. So, for example, like if this is your cricket pitch. So these are the wickets at the bowler's end, let's say. These are the wickets at the batsman end. So the bowler is, delivering the ball from here somewhere. Okay. So what happens is when you take the side view of this, the ball is delivered from somewhere here. Okay, and it goes in what is called a projectile motion. Then it pitches and then it's at the batsman's end. Okay. So basically there is a whole panel on the side somewhere away from the ground that is sending infrared light like this across the pitch. Okay. And on the other side, there is infrared detector. So there's a panel which is the detector. Okay. And there's a panel on this side, which is the infrared source. Okay. So through this now, this network of light falling on the detector, okay, this you can say this is a light field. Right? It's a field of light rays, okay, which are falling on the detector. So literally the detector with light falling on it is able to create a map. It's able to create a two-dimensional map from the side view. You understanding better?
Yes, sir. Sir, I didn't understand the handheld one. This one I understood.
Okay, the handheld one, that works on this thing. That works on the principle of it sends an ultrasonic signal. Okay, so that is something like this, that it has a source of sound, which is ultrasonic. Okay, so an object bounces back the sound.
No, but won't that tell the distance?
Yeah, it will tell. So at a particular instant of time, let's say t equal to t1, it has an echo time. So from that, it's telling this distance S1, let's say. You understanding? Then next moment,
Yes,
the vehicle
sir.
has come here. Okay, so let's say the time is now t1 minus delta t. Okay. Sorry, t1 plus delta t. But that time the echo time will change. So the distance S2 has changed. It has become S1 minus delta S, where delta S is this. Okay. So for the first one, the echo time would be equal to 2s1 upon the speed of sound. Correct now? This is at t1, whatever signal it's sending, because the distance was s1. Okay, but at time t2, which is t1 minus delta t, or sorry, t1 plus delta t, the distance that the sound is traveling is becoming 2 times s1 minus delta s, because the object has come closer by delta s. This distance is the distance moved by the object. Okay, so the obstacle which is sending back the sound, okay, it's like this. So the echo time has now changed to this divided by speed of sound. Okay, so by measuring the difference between this echo time and this echo time, it's measuring delta s. Is it clear now?
Yes, sir.
Yes, sir. So which one is usually more accurate, the infrared one or the ultrasonic one?
Actually, it depends for which type of object. You know, for example, a cricket ball is a small object. So for it, that infrared detector will be the more accurate one.
Okay, so thank you, sir.
Okay. Whereas something like a vehicle is a large target for ultrasonic rays to get reflected by. But also what will happen is if you put a vehicle in an infrared light, light field like this, now it's not like a point object which is moving. It's like a large object which is moving. So it will not be so easy to map. You know, you'll have to design a software that is able to map the motion of different points on vehicles for different sizes of vehicles. So it becomes a more complex business.
Okay.
So I mean, different kind of situations, you want different kind of devices. So that's the general idea. So for example, in air traffic control also, every airport has its radar system, and again that radar system works on the same principle. Or when we talk about submarines, okay, submarines are able to detect moving objects underwater by a system called sonar, right, which works similar to radar, but it's underwater this thing, ultrasonic sound waves. Okay. Now, in complex cases like radar for aircraft application and all that, there is also another aspect which is taken into consideration for calculation of instantaneous speed. Anybody heard the term Doppler's effect?
Yes, sir.
Yes, sir.
Can you tell me what is Doppler's effect?
It's that when an object is like moving towards you, then the frequency that you can hear also increases, and then when it passes you, the frequency you hear decreases.
But then which type of object you're talking about? It's a source of sound, right?
A vibrating
Yeah,
body.
So like you have, for example, a car which is blaring a horn at a particular frequency. So while it is moving towards you, the frequency will appear to be greater, and when it goes past you, the frequency appears to be less, right? So the character of the sound changes as the car moves past you. You would have observed this.
Yes, sir.
Right. So same reason when you are standing on a platform and a train is passing by, train is doing a pass by the platform and not stopping. And while it's doing that, it's blaring the horn. The engine is blaring its horn. So what you'll observe is there's a sharp change in the sound as the train goes past the platform. So again, that happens because of Doppler's effect. Doppler's effect is a very interesting phenomena where if there is motion, okay, if there is relative motion between the source of sound and the detector of the sound, then there's a shift in the frequency. Okay, so that is something that we'll be studying in detail in the chapter of sound. So anyhow, in the case of radar, what happens is that the radar has a sound generator, okay, or a source of sound, okay, and a moving object like an aircraft or something is going to reflect back that sound. So first thing that the radar will calculate is the echo time, the time taken for the sound waves to travel, okay, and reflect and come back. So that echo time will give an idea about the distance at which the aircraft is. But also the radar sensor knows that it's sending the signal at a particular frequency. But if a moving object is reflecting it back, then the reflected signal will be at a shifted frequency. F prime will not be equal to F. And the Doppler shift will be the change in frequency. This is called the Doppler shift. Okay. So this Doppler shift in frequency okay, has a relation with the speed of the moving object. It has a relation with the instantaneous speed v. So that is how a complex radar or sonar system, like the one which is used by air traffic control or by submarines in the case of sonar, it uses a combination of the echo time to determine the distance of the target object and the Doppler shift in the frequency which of the reflected wave to estimate the speed at which, in fact, it's not only able to determine the speed, but it's also able to determine the direction. So it actually makes an accurate measurement of the velocity, that is both the magnitude and the direction of the motion, okay, with respect to where the source of the sonar or the source of the radar frequency or wave is present. Okay, so these are some various different technologies, okay, that can be used. Now coming back to what I was saying earlier, that now we are talking about modern gadgets and all. Now we'll go back in time to around the time Newton was developing calculus and differential calculus. So we are somewhere in the 1600s, and Newton is trying to study motion of different objects, and through that he has discovered his three principles, three laws of motion. That the first law, that the law of inertia, okay, that any body has a tendency to continue in its state of uniform motion okay, or rest until and unless acted upon by an external force. So this describes the property of the body which we call inertia. Okay. So now let's put this in practice in an example situation. So just a while back we were talking about a perfectly frictionless surface, like a well powdered carom board surface, which is, again, you can't say it's perfectly frictionless, but it's nearly perfect. It can have very little amount of friction. So let's assume this is a perfectly smooth surface. So it does not have any friction. Okay. And on that, we have an object which has been given a push. Okay. So it starts moving. So it will have what type of motion? It will have uniform motion because there's no external force. So this object will have a situation where the external force on it is zero as it is moving. Initially it was given a push, but after that, so as it moves like this, let's say this is our x-axis. So it starts from x equal to 0. Now at some time t1, it is at x equal to x1. At some time t2, it is at x equal to x2. At some time t3 is at x equal to x3, and so on and so forth. So if this is the case, it will imply that it will have a uniform motion. So what does uniform motion mean? In terms of kinematics or in terms of its various parameters, what is the meaning of the term uniform motion?
Acceleration is 0.
Yes, very good. We can say acceleration is 0, or we can say, what about the speed or velocity? It is constant or uniform. So it will be moving. So the motion will be with uniform or constant speed along a straight line. Okay. Let's say that straight line is our x-axis. So what will our distance versus time graph look like now?
First,
A straight line will be there.
line.
Yes, very good. Our distance versus time graph will look like a straight line. So for this type of situation where distance versus time is a straight line, okay, if you think in terms of graph now, so this further tells us that speed is constant means that distance is what we call a linear function of time. So what that means is that the distance time graph is a straight line. That is linear. So further from this, what we can see about the distance time graph, that at time t1, if it had covered a distance s1, which is basically x1 on this over here, this distance would be s1, this distance would be s2, and so on and so forth. Okay. So at a time t2, it would have covered a total distance of s2. At a time t3, it would have covered a total distance of s3. Now we can see that the important feature about this is if we calculate average velocity, whether we calculate it from 0 to t1, so that should be s1 by t1, or we calculate average velocity from t1 to t2, that is equal to s2 minus s1 upon t2 minus t1, or we calculate it from t2 to t3, or any such interval, it will always be the same, and that will be equal to the uniform velocity, right? Okay. So that will be equal to this tan theta. It will be equal to the slope of this straight line. It will have a slope of tan theta, which is equal to delta S by delta T. Now that slope only is nothing but the uniform speed. So this type of motion, uniform motion, what important property it has as far as speed is concerned, the average speed for any interval of time will be equal during the motion, and it will be equal to the uniform speed, which is the slope of the straight line, which is representing the distance versus time graph. Right. So hope this concept is clear to all of you.
Yes.
Okay. So you can jot down a quick note about this type of motion. Okay. So if we are taking an example where we are applying this concept from Newton's first law, that if for a body to change its uniform motion, there must be some external force. So that means if the external force is absent, then the motion has to be of which type? It has to be uniform motion. So uniform motion along a straight line, how we describe it in words, we say it covers equal distances in equal interval of time.
Sir,
Yes.
so this finding of the slope, velocity by slope, it is related to integral calculus, no?
Velocity by slope, nahi beta. What is related to integral calculus is something like this, that suppose we had a velocity time graph instead of a distance time graph. Now in this case, of course, it would be a straight line, because the velocity is constant or the speed is constant. But suppose we had a variable velocity in a different situation. We had a velocity which is changing with time like this. Okay. Then how we would calculate the displacement in a certain time interval? It would be this area, right?
Yes.
So the calculation of this area, we will calculate the area in future. This area can be calculated by integration.
So slope will be the differential, right?
Yeah. Whereas if we calculate the slope, and I'm coming to that, the slope at a particular point. So it is the slope of which type of line? It is the slope of the tangent. So if we calculate the slope, it is nothing but delta V by delta T. And that is equal to what? Acceleration. So when we look at a velocity time graph, the slope represents rate of change, which is acceleration. Whereas the area represents what? Area represents displacement. Or if it's speed versus time, it's distance. Whereas when I'm talking about distance versus time, then the area doesn't have any significance.
Okay, sir.
But the slope has a significance, and the slope is equal to what? The speed. Okay, so in this case, it's a straight line. So the slope is same everywhere. So it covers equal distances in equal intervals of time. That means the average speed is the same for any interval during the motion, for any interval of time during the motion. Okay. So in mathematical language, what we will say is that the average speed is equal to the uniform speed, which is equal to the slope of distance time graph. And this statement would be true for any and every interval during the motion. Okay. So just make a quick jot down of this graph and this point if you like, and make sure you understand this thing. Okay.
Sir,
Yes.
sir, if the slope is a curve, then what type of function it would be?
Very good question, and I'm coming to that. Okay. One example would be that it could be a quadratic function. Like here, what is the formula of s distance s versus time t? It is v into t.
Yes, sir.
Okay, but if we have, let's say, a quadratic term, like it is ut plus half at square, where a is a constant and u is a constant, then the graph between distance and time will not be a straight line anymore. It will be what is called a parabolic curve.
Yes, sir.
Okay. Or let's say we have an even more complex motion where some kind of variable force is acting on the body. So if there's variable force, that means its acceleration is variable. Okay, so then we can't apply ut plus half at square. So it is an even more complicated function. But as long as basically there is acceleration, so as long as s cannot be written directly as ut, okay, or vt or whatever, it will not be a straight line. Okay, straight line will be only in that case where the velocity or speed is uniform.
Okay, sir.
So any other case, any case of non-uniform speed or non-uniform velocity will result in a distance versus time graph, which is non-linear, which is not a straight line. Okay. So one practical example of that is the one that I'm coming to next, which is the story of the apple falling. Okay, that is free fall motion. So in free fall motion, we will observe that in equal intervals of time, the distance traveled is not equal. In fact, progressively, for every 1 second interval or every 2 second interval, the distance does what? It increases. So hence we know what is happening to the speed. The speed is increasing. Okay, so finally, one important implication of this is that because the speed is uniform, okay, therefore the instantaneous speed this is also uniform. Okay. So in the case of this situation, the instantaneous speed can be calculated as total distance divided by total time. But this is only when we're talking about uniform motion. That is, we're talking about a motion where acceleration is zero. In that case, the instantaneous speed can be equated with the total distance divided by the total time. So that is what makes the analysis of uniform motion very easy. We don't need to have a speedometer and all that. If we know that our vehicle is moving at a constant speed, we just need to measure the total distance it traveled and divide it by the total time of the journey. That will tell us the speed at any instant during the motion because it was never changing. It's remaining constant. Okay. Now, as opposed to this, if we come to the more complex example, okay, and before that, we will observe the statement of Newton's second law, that the net force on a body equals to the rate of change of its momentum. So since we are not completely into vectors yet, I'll write that in scalar language. So what we'll say is that the net force later we will convert this into a vector equation. So this is not completely a technical equation yet because we have not written it in the language of vectors. Okay, where momentum is mass into velocity. Okay, so if the net force is not equal to 0, that means momentum is not constant. That means velocity is variable or acceleration is non-zero. So an example of such a case would be a freely falling object, a body like an apple in free fall. Okay, so it has a net force acting on it equal to its weight, okay, which is the gravitational pull of the earth. Okay. So as an object is falling like this, okay, continuously the earth is applying the force of gravity on it. And because of that, it will have a non-uniform motion because it will be accelerated. Okay, so now its motion will be something like this. In equal intervals of time, it will be covering larger and larger distances because continuously the gravity is acting on the object, applying a force equal to its weight. So if it's falling towards ground, suppose it was here at t equal to 0, then after 1 second, it might be here. But after 2 seconds, you can see it's covered a larger distance in the next second from 1 to 2. Then from 2 to 3, it has covered an even larger distance. So because it is having an accelerated motion, you can see that progressively it covers larger distances in equal intervals of time. So we say that it is having an accelerated motion. So in that case, its velocity time graph or its distance time graph is not going to look like a linear or a straight line graph anymore, right? It's going to look like a curved graph, but it's curving in such a way that it should satisfy this property which I've shown, that the distances in equal intervals of time are increasing. So for that to happen, you'll see that the shape of the graph, without getting into equations and all that, the shape of the graph will have to be something which is curving like this. So you can see that in equal intervals of time, it is covering progressively larger distances. So if this is a time of 1 second, this is a time of 2 seconds, this is a time of 3 seconds. So you can see that this distance, it is the distance traveled from 0 to 1 second. But comparatively, this distance is larger now because it's the distance traveled from 1 to 2 seconds. This is even larger now. The distance traveled from 2 to 3 seconds. Okay. So that in this diagram, you can see here to here, this is the distance traveled in 0 to 1. Then here to here, this is the distance traveled in 1 to 2. Okay. So this distance is progressively increasing. So that is what this graph is showing. Okay. So now if we make some observations about this graph, we will see that in this graph, we cannot measure instantaneous speed by the slope of any particular straight line right now. Okay. Or the instantaneous speed will not be the same as the average speed. So you can just make a jot down of this part first.
Sir,
Yes.
sir, F net means net force, right?
Yes. Okay. F net
sir,
over here means the net force.
Include
The
That is
air.
the vector sum of all the forces acting on a body. Yes. Yes, tell me, Vita.
So, sir, would it include that friction provided by air?
Yes, yes. Generally, I mean, that type of force is called air resistance, or drag force of the air. Now, that would include that. Okay. But whether that is a significant force or not, that depends on the material of the body. You understanding? Like, for
Yes, sir.
example, a ball made of cotton wool, it will have a significant value of air drag compared to its weight. Okay. So it will have a very different motion compared to, let's say, a stone falling, a stone of high density material, like a piece of brick. If you shatter a piece of brick, the kind of stones that you get, okay, it has high density. So the weight is much larger compared to the air drag forces. So the air drag forces, you can say, are negligible for the case of the stone.
Yes, sir.
So in this case, actually, when I'm showing only mg, I'm assuming that the air drag forces are negligible.
Sir, then in rainfall, it would with the terminal velocity. So the net force would be 0, no?
Yeah, what happens in rainfall is very interesting. Water droplets, they have a significant property called viscosity. Have you heard the term viscosity?
Yes.
Yes, sir.
Yes, sir. Yes, sir.
So viscosity is actually the property of a fluid, like water. Okay, so it has a significant coefficient of viscosity with respect to air. So water droplets moving in atmospheric air, there's a significant drag force that the air applies on the water droplets. Now the drag force, unlike something like gravity, it's not a constant force. The air drag force actually depends on the velocity with which the water droplet is moving. So if this is a water droplet moving with a velocity of v, then as far as the force picture is concerned on it, there will be what we call the viscous force or the air drag force. So let's call that Fd. Now that will be equal to some constant into v, whereas there will be the gravitational force mg, which is constant, which does not depend on the velocity. So initially, when the water droplet starts from the clouds, a kilometer or two up in the sky, its initial speed is 0. So at that moment, what is happening? The drag force on it is 0. Because the drag force depends on the velocity. It is proportional to velocity and opposite in direction. So it has an initial acceleration which is equal to g. So acceleration is equal to g. But as time progresses, it's gaining some velocity. So now it's got some v. So what is happening? Along with the gravitational force, there is the air drag force which is acting. So its acceleration has become less than g, but it's still accelerating downwards. Okay. But at some point of time, it reaches what is called the terminal velocity. So when it reaches the terminal velocity, its acceleration becomes 0. Why? Because the drag force has become big enough to balance the weight acting on it. So when it reaches the terminal velocity, at that moment, what is happening? The acceleration has become 0. So the velocity equal to the terminal velocity now becomes uniform. Okay. And for that to happen, the net force on it must be 0. Okay. So the drag force has to exactly balance the weight. So the drag force is some constant into v. So v into terminal velocity is this. Okay. So this is the constant for the drag force. Now this constant we will see later in a chapter called viscosity. It depends on something called coefficient of viscosity. Okay, it depends on that. It depends on the radius of the droplet. It depends on density, etc. So hope that answers your question partially at least, right?
Yes, sir.
Okay. Okay, now when we observe this graph, what can we note about the instantaneous speed? What can we say about the instantaneous speed?
Constantly increasing.
Yeah, it's not constant, and in fact it's increasing. So what we can observe here is that the instantaneous speed is continuously increasing. Okay. Now, what do we exactly mean by instantaneous speed as far as the graph is concerned? Let's understand that thing next. Okay. So in a graph like this, where the speed is not constant, okay, what is average speed? Okay. And here, when we talk about average speed, we are not talking about the definition. We are talking about the graphical interpretation. Or geometrical interpretation. So let's first talk about average speed, then we'll come back to instantaneous speed.
It would be a secant, I guess, right? Between two far away
Yes,
points.
very good. It is called, okay, it becomes the slope of a particular line, which is called the secant line. Okay. So if this is distance time for a body in free fall, or an object in free fall, for example. Okay. So without going into equations, just logically we have understood that because of the gravitational pull of the earth, the speed is increasing with time. So it's covering larger and larger distances in equal intervals of time. So it's doing this. Okay. Now, if I want to calculate average velocity for time interval t equal to t1 to t2. So these are two specific instants of time. So let's say t1 is a time which on the time axis is lying over here, and t2 is lying over here. So we will define average speed as the distance traveled divided by the time interval. So it is the total distance from the origin or the starting point at time t2 minus total distance from the starting point at time t1 divided by this time interval. So algebraically, this is how I'm defining the average speed for this particular time interval. Now let's see geometrically what that is. So if this is the time t1, then correspondingly this is the distance s1. So on the graph, this point here, let's say this point A, it represents a distance coordinate of s1 for a time coordinate of t1. Okay. And similarly, if t2 is this time, then just draw this vertical line. So this point where it meets the graph, this point represents a distance coordinate of s2 for a time coordinate of t2. Okay. So notice that in this graph now, okay, this here represents my delta t, this interval between t1 and t2, whereas this interval now represents my delta s. That is the same as this line over here. Okay, because this is just a continuation of this horizontal line. So you can see that this delta s by delta t is a sort of slope, but right now we are not seeing any straight line. So we have to draw a straight line joining these 2 points. So if we draw a straight line joining these 2 distinct points A and B, then it will represent the slope of that straight line. Okay. And that kind of straight line is given a specific name, and that name is that it's called the secant line. Okay. So for most of you, might not have heard the term secant line before. So secant line is a line joining two distinct points on any graph. Okay. And therefore, geometrically, our definition of average velocity or average speed in a distance time graphs becomes that it is the slope of the secant line. Right? So you can say that this kind of line, it is called the secant line. Okay. So this angle it's making is the same angle that is making with the x-axis. So we can see that the geometrical interpretation becomes that this average speed is equal to the slope of the secant line tan theta. So our geometrical definition or our graphical interpretation becomes that average speed for interval t equal to t1 to t2. Okay. This equals to the slope of the secant line joining the points at t equal to t1 and t2. Okay. So first of all, what is a secant line? A secant line is a straight line joining any two distinct points on a graph. Okay. So any kind of general graph that we have. So talking in the language of functions, if we have any sort of general curve that represents y as some relation of x or some function of x, then if we take any two arbitrary points on that and join these 2 points with a straight line, that sort of line is called the secant line. Okay. So just make a note of this, quick note of this concept over here. The graphical or geometrical representation of average speed will continue from this point. Okay. Now, next thing, if we talk about instantaneous speed in this case, and we talk about the graphical representation. or the graphical interpretation. So taking the same example of an object in free fall. So we want to calculate instantaneous speed at a particular instant t equal to t naught, let's say. Okay, and that time t naught is over here. So now what do we mean by that? In terms of graphical interpretation. So instantaneous speed will be equal to delta s by delta t, but with a special condition that delta t should be a very small interval of time. The smaller the better. Okay, so let's see how we'll interpret that in terms of the graph. Okay. So let's say this is the time t naught. So this is the point on the graph that represents a certain distance s naught, which it has covered from 0 to t naught. Okay. Now what we'll have to do is we'll have to magnify the graph first of all as much as we can. So let's try that. Okay. So that we are able to draw as small as possible, okay, an interval of time. So let's say I'm talking about very, very short interval of time. So it's very close to this. So then this time interval here would represent delta t, which is very small. Interval. Okay. So correspondingly, this distance it will travel will also be very small. Okay. So these two together would intersect at a point like this. So this would be delta s, which will be equal to the distance in time interval delta t. So as per my definition of instantaneous speed, what it is equal to, it's a ratio of these two. So to understand the ratio of these two, what we will do is now we will draw a separate magnified diagram. We will magnify this. Okay. So when we magnify it, let's say concentrating on that particular point at t naught, okay, the graph at that point is like this. So this particular point of time is t naught, and next to that, this particular point of time is such that this time interval is delta t. So this distance is delta s. Okay. So now, if we join together these 2 points, we'll get a straight line like this. It basically looks something like this. Okay. So on this graph, it looks basically like a straight line, which is like this. So this type of a straight line in particular is called what? It's called a tangent line, because it's almost like joining 2 consecutive points on the graph. So you'll realize that this tangent line, whatever angle it makes with the x-axis, that is the same as this angle over here. So if this small triangle there, I'm magnifying it even more. Magnifying it even more, then you can see that this is my very small delta s in this very small interval of time delta t. Okay. So this particular right angle triangle, it has the same theta that the tangent line is making with respect to the time axis. So it's nothing but slope of tangent. So it's a somewhat more abstract idea in comparison. The graphical interpretation of this becomes what? It is the slope of the tangent drawn to the curve of S versus T at the point T equal to T naught. Okay, so instantaneous speed becomes slope of tangent as opposed to secant line. Okay, now you might say that what is the difference at all between tangent line and secant line, because even the tangent line is the line joining 2 points on the graph. But the point that is that this is just for demonstration purpose. If I'm drawing a perfect tangent line, then the distance between these 2 points should tend to 0. So that means these 2 points that I've drawn over here at T naught and T naught plus delta T, they should actually merge into a single point. Okay, so I'm coming to that. So instantaneous speed is the slope of the tangent line. Okay, instantaneous speed at an instant. For example, T equal to T naught is equal to the slope of the tangent line drawn at the point T equal to T naught on the graph. Okay, so just make a quick note of this or rough note of this and make sure you understand the concepts through the diagrams. Ask me if there's any doubt first, then we'll discuss further.
Sir, but a rate of change actually can't actually be at just 1 point. No, it should have 2 points because like speed is.
Yeah, so you know that is what like the whole business of differential calculus is about. Okay, that it can actually have a value between 2 points which are almost merging into 1 point. That is, delta x is not 0. Okay, so we can't say it's exactly 1 point, but delta x is tending to 0. You understanding the point, Beta?
So they take them as 2 different points, but they're almost very close.
So it's almost like you're taking them as 2 consecutive points. Okay. So it's like if you super magnify the graph, now it will be a collection of dots one after the other.
Yes.
So it's like 2 consecutive dots on the graph. And that's one way to interpret it.
Okay.
So what is the difference between secant line and tangent line?
Yeah, so I'm just coming to that. Okay.
Okay.
So the difference between secant line and tangent line is secant line is a line joining 2 distinct points. But if we draw the tangent line perfectly now, then these 2 points that I've drawn, they should not be distinct. They should be almost merging into each other. You understanding the point, Beta?
Yes, sir.
Okay. So I mean, just to give you another abstract example for this, suppose we are talking about the geometry of a circle. Okay. Talking about a circle. Then any line that we draw like this now, any line that we draw such that it's cutting two distinct points, basically what we call the chord of a circle. Now for the circular curve, we'll say this is a secant line, because it's like a chord, it's cutting at two distinct points. Okay, but on the other hand, if we draw any line from outside like this, which is not cutting two distinct points, but it's just about touching the circle. Okay, so it's at 90 degrees to the radius of the circle at that point. Now this is called a tangent line. Now where it is cutting the circle at, where it is just about touching the circle, now, if we really magnify it, how that should look like. So that will now look like something like this. That the point on that circle magnified a lot. Okay. It's like this point. So you have another point which is very close to it, which is almost merging with the first one. It's like two consecutive points on the circle. Now, if you join those two consecutive points on the circle, then the type of straight line that you will get, that is what your tangent line is. Okay, that is what this whole business of tangent line is. So hope this makes it somewhat clearer.
Yes, sir. Thank you.
Okay. So it's a bit of an abstract concept, of course, and that is why we need a new machinery maths-wise, and that new mathematical machinery is called calculus. Okay, but here itself we can note this point here, that for a perfectly drawn tangent, okay, delta t should be so small that it tends to 0. Okay, so it's extremely small, such that it tends to 0. Okay, so that means the tangent is through two consecutive points on the curve. Okay, so these 2 points over here, t equal to t0 and t equal to t0 plus delta t, okay, they should merge. They should almost become the same. They should almost coincide or overlap. They should be like two distinct points on the curve. I'm sorry, not two distinct, but two consecutive points on the curve. Then our tangent construction will be perfect.
Sir, but in practice, it is actually touching only one point, right? Because that
yeah. So if the 2 points are merging, na, if the 2 points on my graph are merging, then it looks like this, back to the tangent of the circle. You know? Like in the magnified diagram, I'm showing these as two consecutive points. But when I zoom out of it, it'll look like it's just touching the graph at that point anyway. So that's nothing but the perfect tangent.
But shouldn't a tangent touch just at one point? Because that's the definition, only touching at one point. But if we magnify it, we can see 2 points.
Yeah, but the 2 points are almost merged. Na? The distance between them is tending to 0. No?
Okay.
You understanding the point?
Somewhat. Sir.
Yeah. So I'll give you another example to understand this with. Okay. Now suppose you see a digital photograph, a digital image. Okay, in the normal resolution, you see different curves of colors or lines of color and all that. You're seeing the image like this. But if you magnify it a lot, what you will see? You will see pixels of color, individual boxes of color.
Yeah.
So something that appears to be an object like this, when you magnify it enough, you will see that at the edges of the object, you actually have pixels of color, individual boxes of color. Okay, so like that, when you take a general curve, okay, and you magnify any section of that curve enough, you will see that that section of the curve actually consists of individual small little line segments, one after the other. You understanding?
Yeah.
So if I were to super magnify this diagram also over here, I would see that at that point, actually, I have the curve is no longer a curve really. It's more like this, like a collection of line segments, but very small line segments. Now, when I zoom out of this, it will appear to be the normal thing like this. Okay. So if I'm drawing the tangent at this particular point, I have to just extend that particular dash at that point, or that particular line segment. Okay. So that's one way you can visualize it. Or another way you can visualize it, even that a curve like this, when you magnify it at that point, it might even look like this. It might look like a series of steps. So what we are seeing is the outline. So at a particular point, okay, you join it with the other corner next to it. That should form a straight line. So that is nothing but the tangent. So these are various different ways of visualizing the tangent. But algebraically, how we'll say that you are drawing the perfect tangent, that you are actually joining 2 points which are consecutive to each other, and you are making the distance between them tend to 0. So the moment the distance tends to 0, they tend to merge into 1 point. So this secant line, this otherwise what would be a secant line, it now becomes a perfect tangent line.
Okay, sir.
Okay, so it is somewhat of an abstract idea, but we will see that that abstract idea can result in exact calculation when we use the method of differential calculus. Okay. So I know we have completed the time of the lecture, but I'll just take a couple of extra minutes to illustrate this with a point. Okay, so for example, suppose we have a motion along a straight line. Okay. Such that the distance traveled is given by the equation t square. So S is distance in meters, suppose, and T is time in seconds. Okay. Now, first thing we want to do is we want to calculate average speed from T equal to 0 to 2 seconds. Okay. Now, can you tell me how much this will do?
Two meters per second.
Sorry, come again. How much?
2 meters
per second.
2 meters. Yeah, correct. That's 2 meters per second. Okay. Because if we think of the graph of this, we don't need to draw the graph and all, but just for visualization purpose, the distance versus time, the graph will be curving like this because it's t square. So for example, you can see that in 1 second, it's covered a distance of 1 meter. In 2 seconds, it's covered a distance of total distance of 4 meters. Okay. In 3 seconds, it's covered a total distance of 9 meters. Okay. So in equal intervals of time of 1 second, is covering more and more distance. Okay, so it has to have a slope which is rising like this. So this one you will see B average from 0 to 2 seconds will be the distance traveled in 0 to 2 divided by the time interval. So the distance traveled in 0 to 2 you can see is 4 meters. The time interval is 2 seconds. So the average speed should be 2 meters per second. Right. So similarly, if I said here, what is the average speed from t equal to 2 to t equal to 4 seconds, how much would this be now? Quickly calculate and tell me.
Sir, average speed from
6 meters per second.
Yeah, 2 to 4 would be 6, correct?
Yes, sir.
Yes, because you can see that total is 16, but at 2 it was 4. So it's 12 by 2 or 6 meters per second. Okay, so you can see in equal intervals of time. Okay, but now if I ask you, we want to find instantaneous speed at t equal to 2 seconds. Okay, what we want to do now, we want to draw the tangent line at t equal to 2 seconds and we want to calculate its slope. Okay, so how we'll do that? So one is we can calculate instantaneous speed as delta s by delta t by definition, where we take delta t very small. Or in the perfect definition, delta t should be tending to 0. Okay. Now somebody suggest a small value of delta t for me.
0.001 second.
Okay, 0.001. Okay. I would suggest let's start with the easier value. Let's start with delta t equal to 0.01 second. Okay, slightly easier than 0. Later we will take delta t equal to 0.001 also. Now if we take this, let's see what kind of calculation we get. Okay. So we will see that the distance at t equal to 2 seconds is equal to how much? 2 square. So that's equal to 4 meters. Okay. But what about the distance at t equal to 2 plus delta t? It will become 2 plus delta t square. So in this case, it will become 2.01 square. So that will become how much now? It will become 4.0401. Correct?
Yes, sir.
Okay, meters. So now according to this, what should be the instantaneous speed? It should be delta s by delta t. So it should be 4.0401, okay, minus 4 divided by 0.01. Okay, in meters divided by seconds. So it is 0.0401 divided by 0.01. So that is nothing but 4.01 meters per second. Okay. Now change this to this and see what you get. Okay. So again at 2 seconds, this is 4 meters. But now at 2 plus delta t, this is becoming 2.001 squared. So you see, you will get this as 4.004001. Correct?
Yes, sir.
Yes, sir.
So this time what we'll get our V as, we'll get it as 4.004001 minus 4 divided by 0.001. So you'll get it as 0.004001 divided by 0.001. So this time it will become 4.001 meters per second.
Sir,
Yeah, tell me.
Sir, so we are ultimately getting t square plus delta t only, no?
Yeah, very good actually. We are getting t square plus delta t divided by no, we are getting 2t plus delta t. I'll explain now. Okay. But anyway, so what we are seeing is that when we had taken the interval of time to be 1/100th of a second, we were getting close to 4, but with 1 in the second place of decimal. Now, when we are taking 1/1000th of a second or 1 millisecond, we are getting like this. Okay. So like if we continue the series now like this, like suppose we take delta t as 1 microsecond, that is 1 by 10 raised per 6 seconds, we will see that we'll get V as 4.000001. So as we take t smaller and smaller, we'll see that it will converge to the value of 4. So from this, we have the evidence that if delta t is tending to 0, then V will tend to become equal to how much? 4 meters per second. So the exact value of instantaneous speed or the exact slope of the tangent should be equal to 4. Okay, and there's another way we can express this. We can say it like this, that delta s by delta t is equal to 2 plus delta t whole square minus 2 square divided by delta t. Okay. So if I want to make this speed instantaneous, on this I'll have to put the condition. If I want to do the exact calculation, this should be tending to 0. So here delta t should be tending to 0. So if we expand this bracket further, we can see we'll get 2 delta t, sorry, 2t delta t, or rather 4 delta t plus delta t square divided by delta t. Okay. So that we can write as, take delta t common, 4 plus delta t divided by delta t. Okay. Now remember, we are using the condition that delta t is tending to 0, but it's not equal to 0. So if it's not equal to 0, then these two are cancelable. Okay. So this should ultimately be equal to 4 plus delta t. And on that, if we put the condition that delta t is almost equal to 0. Okay. So compared to 4, it's negligible. No? So it becomes exactly 4. So we can see that instead of using numerical values like 1/100th of a second or 1,000th of a second or 1/1,000,000th of a second, if we directly apply the condition that delta t is so small that for all practical purposes it's equal to 0. Okay, then the exact value of instantaneous speed we'll get is how much? It is 4 meters per second. So this is what is showing us that there is a mathematical way of calculating the slope of the tangent. Okay, so this v equal to 4 meters per second, this is the actual slope of tangent at the point t equal to 2 seconds.
Sir, it's approximate, right?
No, so that's what I'm saying now. This one is approximate. 4.01 is approximate. This one is approximate. 4.001 is approximate. Even this one is approximate because I am taking some numerical value of delta t, albeit very small. But now if I take it so small that it's practically equal to 0, then what is happening on my curve, the 2 points which I had drawn to join the tangent line, those points are merging into a single point now. So it's giving me an exact answer.
So, but there is also probability that it might be in a million of a decimal.
Yeah. I mean, like, see, again, million of a decimal still makes it a finite number. No? Even if I say t is 10 raised power minus 15 seconds, so it is what we call 1 femtosecond. Okay, but even in that case, they are two distinct points. Very, very small gap, but they are two distinct points. But when I say it's tending to 0, so then I'm not putting a number on it. I'm saying that it's so small that it's practically equal to 0 only. It's almost equal to 0. So that's when I'm getting the exact value.
Thank you.
Right, understood the point now?
Awesome.
Okay, so it's a bit of an abstract idea because you have to actually imagine that the distance between the two is so small that it's merging into one point, it's tending to one point. But there is a way of calculating it, as you can see, because when we put the condition on the equation like we've done here, that delta t is almost equal to 0, we get a condition on this ratio that delta s by delta t is equal to 4 when I put delta t equal to 0. Okay, so that calculation shows us that it's actually an exact value for that particular condition that the 2 points are merging. And this is like a first example of the application of concept of differentiation, though we have not used the technical language of differentiation like ds by dt and all that. Okay, but we'll see that this is what led to the development of differentiation by Newton. Okay, so solving this exact problem that we want to find the instantaneous rate of change for a distance versus time graph for an object which is moving in accelerated motion. That is what led to the development of differential calculus. Okay, so this is where we'll end today's session. Okay, I will send you the recording and notes very soon, and also eventually I'll send you a small sheet of questions which will analyzing those questions will help you revise today's lecture. Okay, and from this point onwards we'll take it in the next lecture where we'll study more technical definition of differentiation and differential calculus, and from that the formulae and all that of differentiation. Okay, so that's it for today's session, people. Wish you all the best. Hope you've enjoyed today's lecture.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Bye, sir.
Okay, bye, people.
Bye.
Thank you, sir. Bye, sir.
Thank you, sir. Bye.